Hey everyone, and welcome. On behalf of Forge College, I am absolutely thrilled you're tuning into this explainer. If you were hanging out with us for our last session, we were having a pretty fantastic time deploying and testing in the breezy, carefree environment of the Solana cloud, where gas is cheap and mistakes are quickly forgiven. But today, today we're pivoting back to the rigorous, meticulous, and frankly fascinating trenches of Ethereum gas mechanics. So grab those technical pens, because we are moving away from carefree theory and sketching out some serious, structured practice. I absolutely love this quote. From the Solana cloud back to Ethereum, where every single gas penny counts. It really hits the nail on the head. On other chains, yeah, you might get away with a little ad hoc tinkering, just kind of throwing computational resources around like confetti at a parade. But the strict reality of Ethereum, it is vastly different. Messy, unrecorded optimizations simply won't cut it, especially not for your Capstone project. We need proof, we need structure, and we need absolute precision. So here is our game plan for today. Number 1, welcome back to Ethereum. Number 2, the repeatable optimization workflow. 3, creating the artifacts. 4, refactoring the hot path. 5, producing machine-readable proof. And finally, number 6, ready for the capstone. Let's dive in. Kicking things right off with section 1, welcome back to Ethereum, the blueprint. And moving right into section 2, the repeatable optimization workflow, or as I like to call it, the scientific method. Just take a look at the sheer elegance of this 5-step schematic. First up, you identify the bottleneck, finding that measurable metric like total gas for a looped operation. Second, you hypothesize a concrete change. Third, you implement or refactor the code, making absolutely sure the public behavior remains identical. Fourth, you measure using a precise test harness. And fifth, you document. We are moving step by step from spotting a problem to producing auditable, undeniable evidence of our fix. We're effectively treating our code like a rigorous lab experiment. Let's actually define what we're doing here. Gas optimization is defined as a disciplined process of systematic identification, hypothesis, refactoring, measurement, and validation to reduce computational costs. Read that carefully, because an unmeasured change in Ethereum is literally just a rumor. And we are definitely not here to spread rumors. We are here to build mathematical programmatic proof. Okay, section 3, creating the artifacts. It is time for assembling the evidence. Now, you need to produce this exact bundle of files to satisfy your graders and real-world development teams. You need original.sol to show the minimal baseline snippet for direct comparison. You need refactor.sol to document your optimized code and comments. You need your measurements JSON to provide machine-readable gas and opcode breakdowns for programmatic validation. And finally, summary.md gives the one-page human-readable rationale. This whole bundle seamlessly converts your tacit, hey, I fixed it, knowledge into an explicit reviewer-friendly package. But listen, just producing the files isn't enough. They have to be rigidly standardized. You've got to use consistent file names, canonical folder slugs like transfer memory accumulator, and a top-level index file for aggregation. Why go through all that trouble? Because strict standardization across these files is absolutely mandatory, so CI/CD scripts can batch compare your variants without anyone having to manually copy and paste code. Trust me on this, automation is your best friend here, and your future self will thank you for being organized. Which brings us to section 4, refactoring the hot path. The code exercise. Check out our original .sol on the left. We have a storage write happening directly inside a loop. Every single iteration is hitting the blockchain storage, which, as we know, is incredibly expensive. It's like paying a massive toll every time you pass a single mailbox on your street. Now contrast that with refactored.sol on the right. We use an in-memory accumulator, just a local variable, to do all the math, and then we execute one single write to storage at the very end. Boom. We just masterfully slashed our gas costs by avoiding those redundant storage writes. Moving along to section 5, producing machine-readable proof, the JSON log. To extract this proof from our deterministic test harnesses, like Hardhat, we rely on something called opcode efficiency. This is the measurement lens of tracking which specific opcodes changed to explain exactly why the total gas usage moved. It's essentially our shared vocabulary for proving exactly how the refactored code saves money, not just that it saves money. Focus specifically on those S-load operations. Before our refactor, we hit 6 operations. After, just 2.
By capturing these opcode-level counters in our test runs, we generate undeniable evidence. We can definitively prove the exact source of our gas savings, completely removing any guesswork. I mean, you simply cannot argue with the math.
So, all this data goes directly into your JSON log. Your measurements.json file must populate these precise fields: gas total before and after, opcode counts before and the specific test inputs you used. This forms the raw, indisputable data that feeds our validation scripts and ultimately builds the foundation of your Capstone report. But hold on, we must practice proper scientific testing hygiene. Actually, scratch that, it's absolutely crucial. You have to ignore the warm-up noise on your first few runs, use deterministic test inputs and fixed seeds, and I highly advise running your test harness roughly 30 times. Lock those inputs down tight so anyone reviewing your work gets the exact same reliable results. And when you gather those 30 runs, what number do you actually use? The median gas total. I cannot emphasize this powerfully enough, folks. Always use the median to summarize skewed gas distributions. It gracefully filters out the random anomalies and gives you the absolute most honest representation of your code's true performance.
All right, home stretch, section 6. Ready for the capstone, the final checklist.
Here are your marching orders, your exact final checklist. First, pick 3 hot paths from your profiling. Second, refactor each of them into separate canonical folders. Third, run your measurement harness to generate those beautiful JSON logs. And finally, write a crisp, one-page summary per snippet. If you follow these exact steps, you will easily conquer your project deliverable, for sure. But remember, a true master engineer doesn't just brag about their gas savings. You gotta document your trade-offs. Did your optimization increase local memory usage? Did it result in a slightly larger bytecode? Always note the non-gas risks and trade-offs in your summary document. Complete honesty in engineering is paramount. And that sets us up perfectly for our next lesson, scoping and planning the gas analysis report. Let me tell you, arriving at that lesson with structured, JSON-backed evidence makes writing the final report incredibly straightforward. You've already done the hard part. So, I want to leave you with this provocative question to ponder. Are your optimizations just rumors, or can they stand up to the evidence test? Remember, in Ethereum, we demand proof. I highly encourage you to take this blueprint, apply it, and watch your code completely transform. Thank you so much for joining me today. Please be sure to visit the website forge.college to learn more about this subject and explore our wide array of other incredible Web3-related topics. Keep optimizing, and I'll see you in the next explainer.